Lovely to meet you all. Yeah, as sort of Amir introduced, my name is Kate Marshall. I'm a research scientist at IBM Quantum, and I'm also studying for my PhD at the University of Oxford in a theory of quantum systems group. And I wanted to basically talk about this application today. I think the context I had for this meeting was that largely there is an interest in this group in sort of HPC and quantum applications, and this is quite an interesting one for I guess that subject matter, and hopefully it'll be clear by the end of the talk sort of why this is interesting from an HPC and quantum perspective. But what I'll talk about over sort of the next hopefully 30-40 minutes and then leave time for discussion as well, is the main content and results of a recent preprint which is now available in arXiv, titled Quantum Enhanced Markov Chain Monte Carlo for Combinatorial Optimization. And this was a project that was a collaboration between IBM Quantum and then also colleagues of mine who worked at the Hartree Centre, which is a part of the Science and Technologies Facilities Council and part of the Hartree National Centre for Digital Innovation, which was a sort of joint partnership between IBM Quantum and the UK government. And then also we had a collaborator working with us from the Open Quantum Institute as well. So it was very much a collaboration, and a lot of people were involved in sort of making this project happen. And the sort of large sort of overarching point of what I'm going to talk through is a heuristic quantum optimization algorithm that combines sort of three different ingredients, namely quantum enhanced Markov chain Monte Carlo, which is a sampling procedure, is used as a sampling procedure in our case. We also combine that with warm start, QAOA, and parallel tempering, and I'm going to talk through all three of those over the course of the next over this presentation. And I will also show how we used this algorithm to solve maximum independent set graph problems of up to 117 qubits on IBM Quantum hardware. But first of all, I just want to provide a little bit of context behind this project and talk a little bit about where it came from. Please do stop me, by the way, if at any point you want me to talk about something in more detail or I'm not loud enough or anything at all. Yes, so first of all, just sort of a bit of context and a bit of history in this case. A few years ago, a paper was published in Nature that introduced this algorithm, Quantum Enhanced Markov Chain Monte Carlo, and it was from a group of colleagues of ours at IBM actually, which captured some really nice results for this sampling algorithm that demonstrated that if you were to use a quantum proposal distribution for an otherwise sort of fairly well-known MCMC or classical MCMC procedure, if you use a quantum proposal distribution, we could actually achieve up to a quartic speed up in reaching a target distribution more efficiently compared to the classical equivalent of MCMC. This was specifically tested when sampling from the Boltzmann distribution of spin glasses at low temperatures in the case of the original paper. And this was a really nice result. It was the motivation of basically where our work came from, because we were interested to understand whether this sampling procedure, which, as I mentioned, was originally developed for sort of sampling and approximating complex probability distributions, and we sort of had this very native and tangible resilience to noise on the device, and we wanted to know if this could be applied in the context of combinatorial optimization. So in order to set us up nicely, just to make sure we're all on the same page, I'll just briefly describe what the sort of need-to-know parts of classical and quantum enhanced Markov chain Monte Carlo. I'll talk about this very generally, and then we'll talk about how this is used in our algorithm. And we'll also discuss sort of results of how we use this algorithm to solve different optimization problems. And then I'll close up with a bit of a discussion as to why this is relevant to an HPC and quantum context as well. Yes, here's the motivation. So can QMCMC be useful in the context of combinatorial optimization? So for those that might not be familiar with classical or quantum enhanced Markov chain Monte Carlo for that matter, we'll start from the fact that you might be familiar with the fact that constructing and classically sampling from low temperature Gibbs states is considered to be a computationally hard task. This is because it involves exploring sort of exponentially large configuration spaces. And classical MCMC is a technique that's been used for the best part of the past century for approximating these Boltzmann distributions without explicitly computing the computationally hard terms like the target distribution and the associated partition function. And the way it works is sort of generally described by the sort of drawing I've got on the screen just now, where we take some initial spin configuration and we sort of sample this sort of starting point, and then we sample a possible transition to a new spin configuration in this case, and we evaluate that proposed transition using a classical acceptance criteria, which chooses whether to accept or reject that transition. And then over time, after many steps, we start to build up a picture of what the distribution looks like for this system at a given temperature over all possible configurations. So we can see in this diagram how sort of the chain of samples is either accepted or rejected. The rejected ones are visualized in red here. And over time, we start to build up this chain, this Markov chain of accepted proposals, which evolves through the full space of possible spin configurations. Another way to think about this is to think about it as like building a dense matrix of all possible proposed transitions, Q, from some initial state S to S dash. And from this, we can build up another dense transition matrix P, which is the product of Q with this acceptance term. So we have this sort of two-part classical, we have a sort of two-part procedure where we have possible transitions, and those possible or proposed transitions are evaluated against an acceptance criteria, which then determines whether or not those sort of transitions actually do happen and the probability of which they do happen. These different acceptance terms can basically take many, many different forms, and the most notable and perhaps the one most important to us because we use it in our work is the Metropolis Hastings criteria, and the definition of this is sort of visualized on the screen, but we're not going to go into too much detail as to how this is composed because it's not the main point of the work here. But we can think of these as the sort of key ingredients to how we actually build up these possible transitions and build up a picture, how we use this to build up a picture of maybe the problem that we're trying to solve. So in this case, sampling from a complex probability distribution. And the definition of this matrix P in this case, it's made statistically rigorous by this detailed balance condition, which I can talk about if we're interested, but if not, it's not sort of of huge importance to the work that we do. But this essentially guarantees that over time, matrix P does converge to the target distribution that we want. So that's a very sort of high-level introduction to how the classical MCMC procedure works. And in quantum enhanced MCMC, the authors essentially propose that these transitions be generated by a quantum device. And now this is very well motivated because we can actually think of sampling from a quantum circuit as a native way to sample from a distribution that we're trying to approximate, provided that the circuit actually represents our system of interest. So we use a quantum computer to build the proposal matrix Q, and then the proposals are still actually evaluated classically. So we end up with this two-part hybrid quantum classical proposal and evaluation procedure. And we managed to sort of maintain this detailed balance if you're interested, because we sort of take advantage of the fact that we use these symmetric circuits that ensure that the probability of a transition is equally probable to its reverse transition. And that means that we can actually show a cancellation in the ratios of sort of the different terms here. And this means that we can actually maintain the detailed balance that's so important to sort of any MCMC procedure. And we can demonstrate that in the quantum enhanced case as well. So in this case, the ratio of Q in our acceptance term cancels, and it makes the computation of our sort of classical acceptance term tractable. And we can actually run, we have a statistically sort of rigorous way to run a quantum enhanced Markov chain Monte Carlo procedure using a quantum device to sample or provide the sort of sampling engine for the proposal distribution. And when sort of analytically evaluated, the authors of this paper were able to claim up to a quartic speedup in convergence to this target distribution. And small-scale tests were also run on quantum hardware at the time with a handful of qubits. So this was sort of a really nice demonstration of a piece of work which seemed to show sort of tangible resilience to noise, even on sort of near-term quantum devices. But I guess it sort of was a really, really nice piece of work that wasn't really applied to any sort of large scale problems since it was published a few years ago. So this is where sort of our motivations came in, which is obviously we've seen now how QMCMC might be a nice tool for sampling, but where does optimization come in? So our goal is slightly different. Instead of trying to converge to a target distribution and to do this sort of approximation task, we actually want to converge to a global optima. So that might be defined by a QUBO, for example. And in the classical world, Markov chain Monte Carlo is a classical technique because it has actually historically been employed within sort of these simulated annealing and parallel tempering frameworks. to find ground states of many body systems. And so we've already seen sort of in the classical world examples of using these MCMC procedures in an optimization-like context. Now I can describe that, for example, at a very high level, simulated annealing would use a classical or a quantum enhanced Markov chain, sort of either of them in this case, to sample a candidate transition, or in this case, solution to an optimization problem, from a temperature control distribution, and we would gradually lower that temperature such that we increasingly concentrate the probability mass on sort of low energy or high quality solutions until we converge to our global optimum. This is one way that we can employ sort of these MCMC-like procedures as a sort of sampling engine to drive solutions towards an optimization problem. And this is sort of done by gradually guiding or biasing the sampler towards a good solution via this temperature parameter. But in our paper, we actually employ parallel tempering. So I'm going to talk a little bit more about that one instead. And this one works slightly differently. In this case, we actually operate sort of multiple copies of a circuit or an experiment in parallel, and they're all operating at various temperatures. And these aren't sort of physical temperatures. This is sort of like a tunable parameter that changes the shape of the distribution that the individual experiments are sampling from. Now, in this sort of like rather messy image here, I've got 3 different circuits that are sort of identical in everything except the temperature in which I'm sort of allowing to sample from. And I'm sampling from them sort of in parallel, and I allow the different experiments to actually exchange information at different points in time at regular intervals. And this means that we can actually swap the proposed solutions to the optimization problems between neighboring chains at regular intervals. And this means that if we have a really rugged optimization landscape with many high energy barriers, it means that the hotter temperature chains will be sort of more aggressive in their search pattern. They're more likely to jump around a lot. And where a low temperature chain might be sort of more closely tracking local minima, but equally they're more likely to get stuck in local minima. It means if we allow them to exchange information, you can actually sort of find a way that higher temperature chains are able to lift low temperature ones out of local minima. And together they're sort of, you come up with this robust framework where you have this team effort in order to sort of solve an optimization problem that any one of them wouldn't have been able to as efficiently solve on their own. So you end up with this sort of, you're still sort of using that temperature parameter like in the simulated annealing context, but in a very different way by operating multiple experiments in parallel, where each of them have sort of a different job or a different responsibility to help each other explore the optimization landscape. And this is the framework that we use in our paper. And actually this visualization here is a nice visualization of the algorithm that we built. So some other key points to understand in order to sort of fully understand the algorithm that we put together for this purpose of solving optimization problems is that, first of all, this sort of QMCMC context of using sort of these different circuits as sampling engines to provide potential solutions to our optimization problem. We then operate them in a parallel tempering context where there's sort of multiple of these experiments operating in parallel and working together to propose different solutions to a problem. But then the last piece is essentially, it comes from the fact that our QMCMC circuits actually look a lot like QAOA. And if you're familiar with QAOA, then this part will be more interesting to you. And if not, then don't worry. It'll sort of all come together at the end. But we start with the fact that in the original paper for the QMCMC work, the Hamiltonian looked like sort of a discretized annealing Hamiltonian. It looks a lot like QAOA, but not exactly like QAOA. And this is sort of our starting point. And if you actually take a first order Trotter decomposition of this Hamiltonian, we can actually find that the resulting circuits look a lot like QAOA, but with static beta and gamma parameters across all sort of P layers of the QAOA circuit. In the original paper, the authors were much more interested in sort of time evolution experiments. So they were worried about Trotter error and they took a second order Trotter decomposition. But in our case, because we're not so concerned with Trotter error and we're not trying to evolve these circuits for long periods of time, we can actually take a first order Trotter decomposition. And that's very convenient for us because it means that we can treat the circuits like QAOA circuits. And since we do have circuits that look like a lot like QAOA, this means we can take advantage of the wealth of different sort of resources that are available for running QAOA circuits at large scales on the device. So there's sort of a wealth of capabilities available, not just through IBM tools, but through multiple different sort of organizations that have produced tools to help with QoA parameter optimization at utility scales, for circuit compilation tools. Within the IBM infrastructure, we have lots of sort of ways to efficiently compile QoA circuits onto our devices using sensible sort of mappings and routings techniques. And essentially, we're able to take advantage of all of these different capabilities to run the largest QoA circuits we can on the device. The last thing to mention is that the sort of last ingredient to the algorithm and how we piece it all together, which is this warm starting QoA piece. And sort of warm starting QoA draws upon like the analogies of what we actually do a lot in the classical optimization world, which is that we want to leverage good solutions to an optimization problem. And essentially, by one way to do this, or one way to accelerate an optimization algorithm, is to take something that we know is somewhat good and initialize the algorithm sort of to say that we know this is quite good, but we think that maybe you can do better. And in this case, you can sort of accelerate the progress of these algorithms by sort of warm starting them. And this is a very common practice in classical optimization, and there's lots of literature available on how you can do this in a quantum optimization context as well. So we used a very basic implementation of what warm starting QoA looks like, and we essentially sort of warm start our iterative QMCMC circuits by composing steps of the Markov chain by warm starting our algorithm with a good solution taken from the sampling procedure of the previous iteration of circuits. So this is fairly standard in sort of quantum optimization as well. And when we pull all of these together, we come back to this image and back to sort of the high level view of our algorithm, where in summary, we're sort of taking QoA circuits as our proposal mechanism from which to sample our sort of candidate solutions or transitions. And because we intend to run on hardware, we actually take many samples per step, and we do some sort of very basic noise mitigation. This is actually interesting and notable because in standard MCMC, you would really only take one shot or sample per iteration. But of course, we're working with real quantum hardware in this case, so it's not really possible to take one shot per iteration. We have to take many and then choose a sort of what the best attempt we can, a noise-free shot. So there's a bit of a limitation there with the fact that we're working with noisy hardware. And then we evaluate our proposal using this classical accept-reject step. In our case, we use this Metropolis Hastings acceptance criteria. And we also offer these regular exchange intervals between replicas. And finally, we use the accepted solution or configuration to warm start the next series of circuits from which we sample. And so in this very sort of high level graph, we can see that there's iterations sort of plotted on the x-axis here against the objective value on the y-axis. And we can see that this red chain is sort of jumping around a lot more. But it's actually able to reach a somewhat sensible solution the quickest because of its sort of more aggressive search pattern. And then every time the chains cross over, that's representing a point in time where neighboring chains are allowed to exchange information. So it passes this information down the temperature ladder, as it were, to give it to a slightly more conservative chain, for lack of a better word, which is exploring the cost landscape sort of less aggressively, and that sort of information gets passed down again to the coldest chain in this case, which is represented by the blue one, and that blue one has a sort of a higher chance of sampling around those good solutions to come up with eventually the global optimum in this case. And we tested the performance of this algorithm on a specific type of graph problems, which were maximum independent set graph problems. And these are a family of NP-hard combinatorial optimization problems where we seek to find the largest possible subset of vertices of a given graph, where no two vertices share an edge. So you might already be aware of the fact that the majority of the quantum optimization literature to date is made up of analyzing these QUBO problems, or quadratic unconstrained binary optimization problems. Naturally, constrained optimization problems are meant to be a little bit harder, which was a motivating factor for us in this case, but also there had been a lot of effort previously to when I started this project, where a lot of colleagues at IBM had built up some really useful tools for mapping these types of maximum independent set problems to our heavy hex hardware. So that was another motivating factor to me, was partly the fact it was a little bit harder than a standard QUBO problem, but also it was we had lots of tools out there for exploring these problems at large scales, at utility scales on the device. One other sort of motivating factor to mention is the fact that we have this, also we just sort of note here that when we have our Hamiltonian of this form, we can define the problem as a maximization problem. We actually flip this to a minimization problem before we build our circuits and start sampling solutions, but we can see here how this is an easy sort of flip. And we see our problem becoming essentially a balancing act of trying to balance the objective versus the constraint terms. So this lambda or Lagrange multiplier term acts as a penalty to discourage sort of bad solutions that violate the constraints we've provided. But essentially, we can do this sort of parameter choice as part of a pre-processing step before we run on the hardware. So we can do a lot of sort of classical optimization and parameter tuning to find good values for these different terms according to the graph that we've encoded in the problem that we're looking at. But one other reason that it's sort of attractive to use these MIS problems in our case was the fact that we had this sort of benchmarking library. It was called the Quantum Optimization Benchmarking Library. And this meant that we had a lot of sort of different graphs available to test on the device that we knew were non-trivial. So as you can see the graph on the screen right now, we could hardly call that hardware native, at least for the superconducting hardware that we use at IBM. So we thought that this was a nice meaty problem to try and something that we were aiming for at the beginning of the project. And we sort of took this example from a bank of different graphs that were available from this optimization benchmarking library, which is sort of home of a number of different sort of interesting problem instances to benchmark quantum and classical optimization algorithms against. And these problems are sort of generally quite relevant to a number of different industrial problems in financial services and molecular biology. So it seemed like a relevant problem set to be focusing on. The sort of, I guess I can jump over to how we actually tested this on an example one. So in the case of this 117 node graph that I mentioned here, we solved essentially, we look at the maybe if I flick back to this drawing, you can see the similarities here between the different experiments running in parallel and exchanging information at different intervals. In the sort of real result here of what they running this experiment for the 117 node graph look like when we run it on device, we see that we have 6 different sort of copies of our experiment, all working in parallel at different temperatures. And we see the hot and cold chains essentially working together, regularly exchanging information until eventually, in this case, the orange chain, which is the second coldest chain, converges to the target objective or the global optimum first. And it's sort of, you can see how many times these lines cross over because they're allowed to sort of exchange information at regular intervals. That's how we see that they're exchanging information and essentially helping each other out. Now, sort of one thing I'll note here, because it's very relevant to the hardware side of the experiments that we were running, you may already know that when you sort of look at these sampling-based experiments, we don't benefit from the sort of suite of error mitigation techniques and tools that are available when you use sort of expectation value-based experiments. But there was sort of a very clever trick sort of released previously to when I was doing these sort of hardware experiments, where some IBM colleagues recently demonstrated that the easiest way to mitigate against noise on a near-term device for sampling experiments is by taking more samples. So this is what we did. Generally, in the experiment here, we took 10,000 shots per iteration. And where we assume that noise sort of worsens the quality of our results, we essentially do some filtering where we discard the sort of really, really bad ones of these and keep only the low energy proposals from the device. And then we subsample from the sort of an arguably noise-free portion of those results. This result itself was actually performed on our IBM Boston Heron R3 device. And we can sort of compare actually the scaling behavior as we look at different instance sizes of these graphs and actually different hardware examples as well, so different devices on the hardware as well. So I'll look at 2 different types of scaling behavior here. So just quickly to sort of be clear about what we're looking at here, there's 5 different sets of points on each color of the plots that you'll see on the next 2 slides. That represents 5 different graphs that we looked at. Of course, in an ideal world, we would look at hundreds of graphs. Generally, it takes quite a lot of time to tune the parameters and to find that sort of Lagrange multiplier term I alluded to earlier, and essentially the simulations for these quantum circuits, because they very quickly become sort of over the point where we can sort of exactly simulate the behavior of the quantum circuits. We actually use quite a lot of HPC to both tune the parameters for these circuits, but also classically simulate what the experiments will look like, and then also simulate the classical sort of versions of our algorithms. So we only looked at 5 different problem instances in this paper, which is something that I think is very important to highlight, because our results are very, very early indicative, and you can't draw too many conclusions when you only have 5 points on a line. So just putting that out there, that it's a known sort of, we would have loved to have studied more, but it took sort of over a year to eventually put these 5 different hardware experiments up together of up to 117 nodes on 117 qubits on the device here. So we can see here 5 different points for each sort of implementation of the algorithm that we explored. And in this sort of first example of the sort of scaling behavior that we're probing in this case, we compare to a classical benchmark. So in this case, the orange line on the plot is representing a classical variation of our algorithm. So we're using a classical bit flip proposal strategy to be our sampling engine in this case, and we compare it to a simulation of the quantum circuits. And the reason that I'm simulating them in this case is because we wanted to be as true as possible to the one shot per iteration sort of framework that's standard to classical MCMC. So we wanted to only take one shot per iteration, but of course we couldn't feasibly take only one shot per iteration on the device. So we tried to implement a noise-free simulation, which is very hard when you're working sort of in these 117 qubit scales, but we tried as best we could to simulate this using sort of tensor network simulations, and we simulated the one shot per iteration sort of behavior here. And what you can see is that the classical implementation of the algorithm outperforms the blue line, the quantum implementation of the algorithm, in the 5 problem instances tested here for the one-shot variation of this. However, if we then look at the many-shot variation and implement this on the device with this sort of noise mitigated version of this experiment, we see something slightly more exciting, which is that in the earlier instances, all of the different variations of the algorithm, both tested on hardware and in simulation, we see that all of them sort of are equally performant. In the first plot on a line, all of those points are overlapping, so all of them sort of converge in the same time frames. But we do actually reach a scale where both the hardware experiments are able to sort of outperform what we saw in the simulations of the quantum circuits, but also in with the classical proposal strategy as well. Now, the one thing that's important to note here is that we're comparing this multi-shot setting to this one-shot setting. So one thing to check was that massively benefiting the quantum experiments? And one way to sort of have a look at that is to see how much the classical experiments sort of benefited from this multi-shot procedure. But we were able to see that in sort of comparing the one-shot to the multi-shot procedure, both the gradient and the sort of time taken for these examples to converge didn't change for the classical procedures. Hopefully that doesn't sort of bias our results too much. But one thing that's interesting is the fact we were able to sort of see better performance on the hardware than we could with our MPS simulations. And that essentially doesn't indicate anything close to quantum advantage, because this is a very sort of specific type of algorithm where sort of classical suites like Cplex and Gurobi would be able to solve a problem like this in seconds. But for a similar sampling procedure to what we're testing, in this case, it's interesting to see that the truncation error of the MPS simulations of the circuit seemed to actually become more detrimental than hardware noise at one point. And you can see that sort of happens around the 60 plus qubit scale, which is interesting to see in practice. So that was a really nice result. And you can see here also a very a nice gradient and sort of the improvement that you can see from one type of device to another. So we tested 3 different generations of the Heron devices, and the Heron R3 devices are significantly more performant than the Heron R2 and Heron R1 of the same sort of family of devices. And that's quite nice to see in practice as well.
Sorry, I have a question here.
Of course.
You might have mentioned it. I joined a bit late to this talk. It's not clear to me what the classical algorithm baseline is. In general, one of the things that I've seen consistently across the industry when we benchmark quantum optimization, we benchmark against the strawmans that are like classical. It's not the fair classical counterpart. Could you just explain that to me?
I might need you to repeat that second question, but with regards to your first one, the classical sort of counterpart from this would be looking at so we extended a classical MCMC procedure, which would use in the classical sense, it would sample from a classical sort of proposal distribution. So for example, just a bit flip strategy, if you start with some random bit string and you allow a certain number of flips per sort of iteration of your experiment, you can start to sample possible transitions. For example, in this case, they were sort of sampling from low temperature spin glasses, so they were looking at spin configurations. In our case, we were looking at optimization problems, so our sampling procedure would be sampling possible solutions to an MIS problem. And in the classical version of this, we would just use a sort of classical distribution to sample from, so some classical bit flip strategy. And in the quantum variant, we're actually sampling directly from the quantum computer, which is drawing from a circuit that's representing the system that we're trying to approximate or sample from. So
So,
the
so sorry, I'm trying to express is that you're basically comparing a QA/OA type of algorithm and quantum circuit against a standard MCMC baseline with Metropolis Hastings update over some uh, probability distribution that you would like to sample. Is that the case?
we are comparing a heuristic quantum optimization algorithm that's based on quantum enhanced Markov chain Monte Carlo, and then also uses some sort of QoA-like techniques, but the algorithm that we use isn't directly QoA, no. We're using a
Yeah,
quantum
but
enhanced.
yeah,
Sorry.
but I think there are variational probabilistic computing algorithms that mimic the QAOA, and if you benchmark against those, I'm saying a standard plain vanilla MCMC is not the corresponding baseline. It's not the fair baseline.
Yeah, so
You
that
can,
wasn't.
yeah, that's the what I'm saying is that generally people compare against simulated annealing or like uh, MCMC updates that are homogeneous in nature, and they don't have variational aspects, or they cannot have local temperatures. And basically quantum on the other side, we allow quantum to have uh, the ability to learn rotations locally, and just basically having in a way quantum fluctuations can be a space-time um, adjusted in a way that optimizes like it creates a, let's say, shortcut to adiabaticity if you want to compare QAOA to a quantum annealing, but we do not allow a classical counterpart to do that. So it doesn't necessarily indicating the results. If you don't have the correct classical counterpart, it won't necessarily would be a signature of quantum advantage.
Yes, so that's a really good description of sort of QoA style experiments. In this case, we're not looking at that. We did also benchmark against QoA, but the QoA circuits, sort of in their most vanilla sense, were not able to solve the optimization problems that we were looking at beyond the 17 qubit example directly. So that's why we were sort of looking at ways that we could build an algorithm that sort of took inspiration from QoA, but was not sort of QoA exactly. So we didn't do sort of the usual variational procedure of what you're describing, where we tune sort of QoA parameters to match the sort of problem structure here. We did that as part of a sort of an inspired version of that as part of a pre-processing step, so that we could get sort of a good initial solution. But QoA in its most vanilla sense wasn't able to, at least in the case where we were using a p=2 layer QoA, wasn't able to solve the problem instances that we were looking at beyond the smallest problem that we looked at, which was 17 qubits. The next size up was 52 qubits, and we were not able to solve that on the device within the sort of framework that we were working in, for a p=2e layer QI, we would probably need higher level layers of p to compare against that.
Okay, thanks.
No worries. So yes, so in this sort of sense here, when we're looking at probing the scaling behavior, we have two different comparisons. One of them is sort of by taking a direct replacement of our algorithm, but replacing the proposal distribution to be a classical bit fit strategy. And we compare it in the sort of one-shot case, and then we compare it again with some both in classical and quantum simulations again. But in this case, with the 10,000 shots per iteration, we can also do that on the device. And we see some sort of very interesting early behavior on how this problem scales up. So again, just to reiterate, this is not something that we would sort of indicate as claiming anything like quantum advantage in an optimization context. Very advanced sort of classical optimization suites like Cplex and Gurobi are able to solve all of these problems to optimality. But the idea is that there are smaller problems than you might think within the maximum independent set family, even as small as sort of a handful of hundreds of nodes, which have not been solved to optimality with Cplex and Gurobi. So those would be an interesting sort of problem case to look at if we were able to look at sort of simulating circuits in a similar way to how we do here, with devices that have more like sort of up to 1,000 nodes. Or a few hundred nodes at least. So this is something that is a very early indication of something that could be quite exciting, but there's no sort of demonstration or claim for something that we could do beyond what classical solvers can do at their sort of best possible strengths. So I guess the last thing I sort of wanted to mention was that in sort of future work, we're obviously looking to sort of solve much larger problems, as I sort of alluded to there. This is a problem family that's considered NP hard and does have relatively small problem instances that are not solved to optimality, even with sort of advanced classical solvers. So that would be an interesting problem case for us to look at as sort of device sizes scale. But then furthermore, we're also looking at ways that we can maybe be creative with sort of division of graphs across multiple devices or chips, for example. If there are sort of ways that we can look at decomposing graphs and solving portions of those graphs on different devices, this would be very interesting. And as you've seen over the course of hopefully this talk, you can see that there is very much like a parallel nature to this algorithm. And as sort of device sizes and graph problems that we want to tackle scale, this is something that we sort of do imagine becoming something that's requiring more and more parallelism, and that sort of is in some way interesting for an HPC and quantum conversation. But probably the more interesting or sort of obvious point from an HPC and quantum perspective is that if you've ever worked with quantum enhanced Markov chain Monte Carlo before, or equally if you've not, there's perhaps a long-standing assumption that HPC and quantum resources are needed to run these QMCMC experiments at scale. This is largely because of that inherently quantum classical workflow due to the continuous exchange between sampling from the quantum computer and evaluating that sort of sample or set of samples, thousands of samples, potentially classically, with that acceptance criteria. And we were sort of surprised that in this project, we were actually able to run these QMCMC experiments without HPC capabilities for the runtime of the experiment. We needed it we used sort of cluster capabilities for both simulations of our quantum circuits, parameter optimization, and benchmarking with classical MCMC variants. But generally, we were able to avoid using HPC sort of in the sort of runtime of the experiments, largely because we were able to do a lot of pre-processing for our circuits, and we were able to figure out sort of clever ways to just parallelize in a very sort of simple way on local devices the sort of error mitigation over thousands of shots and the subsampling procedures. But it is something that we expect will become sort of relevant for much larger problem sizes, and this sort of tight coupling nature of why you need sort of classical and quantum resources locally located so that you don't have introduced delays into these quantum classical exchanges during the runtime of the experiment, because as you perhaps noticed before, the previous iteration of these quantum experiments directly determine what's next run on the device. So you do need to sort of ensure that you're reducing latencies as much as possible, such that the sort of experiment time that you reserve the device for is as minimal as possible due to the scarcity of these quantum resources. So it is something that I do think it's important to point out. I think a lot of people that work on QMCMC imagine that you have to use HPC and quantum resources even for the scales of problems that we can run run today. In this project, we were actually able to run QMCMC experiments of up to sort of 120 qubits without that, but it is something that we imagine would be needed if we were looking at problems of sort of thousands of nodes, which are sooner than we might think. And that sort of concludes everything that I wanted to talk about, but super happy to answer questions or go into any points that I sort of alluded to in more detail, as is of interest to the audience.
So I just want to follow up on the earlier question I had, is that
Sure.
I want to I put in the chat a couple of papers on non-local Monte Carlo algorithms that are classical. These are a different kind of baseline compared to PIAOA, that's a probabilistic approximate quantum approximate algorithms, which are kind of mimicking QAOA. There's a Nature.com paper on that. You can find that, but it's a different class. It's just actually improving MCMC with non-local move, which instead of doing a tunneling, you identify a subset of variables that could basically keep you hostage in a Bayesian of attractions and do a collective, so you increase the temperature locally for those subsets of variables, and you can escape, basically do we could say quantum inspired tunneling, but you do it entirely classically. There's no quantum at all. There is no quantum subrouting, and they perform better, certain solving SAT problem near computational phase transition. We find orders of magnitude improvements. So you might want to consider this. I'm saying that
Yeah.
for claim of advantage, the bars could be much higher than what usually people think.
Yeah, definitely. Again, I think that, yeah, that's a paper that we came across that we actually did sort of implement a version of it too. It wasn't quite as competitive as just like literally vanilla bit flip strategies in this case. I think just because of the way that we're sort of running, we're not sort of variationally improving on the circuit, so we're sort of restarting them every time. But it was definitely a very interesting approach. And I think that, yeah, obviously we weren't sort of looking to make any advantage claims as part of this, but I definitely think that it would be a very good reference point for sort of future, any sort of advantage scale experiments of this nature, definitely.
Okay.
Russ, go ahead.
Can I ask my question? Sorry, I didn't hear.
Yeah, go ahead, please.
Okay, thanks for the talk here. That was very, very interesting. One thing I missed, I think you did say, was on the examples you could handle, did you actually reach the classical optimum? And if not, how close did you get?
Yeah, so in all of the instances we tested, we reached the classical optimum as verified by, we use CPLEX as our baseline to know whether we'd reached the classical optimum, but it was reached in every case.
Right, so you're just bounded by qubit number, basically.
Yes, we didn't. We used a device that had like 127 qubits, and on the benchmarking library that we were drawing the examples from, they didn't have. I think the sort of the window that we were looking in, at least 117 was the largest that we could fit on the device. That didn't look hardware native. It was important for us that we didn't pick something that looked like an easy problem for the heavy hex.
Yep.
So yeah, for the family of sort of animal social interaction networks, this was the largest ones that was available.
Great, thank you.
No worries.
I have a question regarding approaching this a little bit from the HPC classical perspective. You talked a little bit about parallelism and distribution and data exchange. Can you maybe dive a little bit deeper into this? When you talk about parallelism, you're executing different circuits, so the circuits can run in parallel on different quantum computers if necessary. But did you also mean classical parallelism? And for the data exchange, I didn't quite catch what data is being exchanged and how are they being exchanged.
Sure. Yeah, that's a really good question. So yes, in the most basic sense, you can the idea for parallel tempering generally is that we would run each of these experiments on ideally in parallel on either one large device where that we subpartition somehow, or on different devices, which is much easier than partitioning. But generally, we actually only had access to one device for the duration of this experiment. So we did run them in sort of one after the other, but then sort of allowed them each the interval after the sampling procedure had been completed. This exchange process that I'll go into more detail in a second. But in an ideal world, we would run this actually in parallel, and that would reduce the amount of time that we spent on any one device. So this would be more cost effective if we were to run this at scale. We also only ran up to sort of 6 parallel experiments in this case because we wanted to try and keep things as quick as possible. But if we were able to either sort of run this in parallel on one large device or across many devices, we would have been able to run much more parallel experiments. So it's definitely sort of a very parallel problem by nature. And the classical sort of parallel side is that there is a sort of, I alluded to this like very basic noise mitigation strategy that you use for sampling experiments, where you take multiple samples per experiment and then filter for noise. That is a sort of post-processing procedure that comes after each of the sampling procedures on the device happens. So you would take sort of many thousand samples and then run sort of a sampling procedure following that. We actually were limited to how many samples we could take per iteration, again, because of device time and because of our classical processing power that was available to us. And it still worked okay. So it wasn't really a hugely motivating factor for us to try and scale that part up. But obviously, the idea would be that we would take as many samples as we possibly could, because that would mean that we would get better and better results. And that would require sort of that classical post-processing stage to happen in parallel for each of the experiments that you've run. The exchange portion comes as like a post-processing procedure to even that, which is that the error mitigated solution that's sort of accepted by the acceptance procedure, which you can sort of imagine is part of that first post-processing stage. Once you've accepted a solution, you then allow the different parallel experiments to swap that solution. So that means that if the hotter experiment got a better one, it would likely be swapped with the colder chain, and then the hotter experiment would actually inherit that worse solution to the optimization problem at that point. So they directly swap their solutions, and then they continue, and you warm start the next iteration of circuits based on whatever was accepted from that previous chain. So it's almost like a two-step post-processing procedure that's done entirely classically before the next iteration of experiments can happen. Is that clear?
Yeah, and the classical post-processing here, you mentioned that you didn't require HPC resources, like the requirement was low, so there isn't all the classical post-processing occurring. Okay.
Yeah, in this case, because we weren't able to take, for the length of time that we were using on the device, there was sort of we had to be a little bit conservative with how many shots we could take because of limitations sort of imposed by our devices. So we only took 10,000 shots. So there was only a couple of seconds of sort of like post-processing time. But you can imagine for a much longer experiment or for many, many more shots, we wouldn't have really been able to just continued to do this on sort of using the framework I was working with, which was we were trying to avoid using HPC at the time because we didn't have the framework to use it within the runtime of the experiment. But it would be interesting if we were solving a much larger problem and taking many, many more thousand shots. 10,000 isn't that many. So you could take up to sort of 10 million shots if you were just running a one iteration experiment on the devices today. But we were trying to minimize the amount of time we were taking since our algorithm takes many sort of iterations at a time. Hopefully that makes sense. But yeah, I think this would very quickly become quite intensive if we were to continue sort of trying to run it on local machines.
Fair. One last bit, and then I'll switch to Ross. Like when you ran 10,000K shots, how long did that take on the machine? Like what was the time scale?
That was on the scale of seconds. So it was about 3 seconds per experiment. But then you can imagine there's 6 in parallel, and they're each happening in series in our case. So you can add it up, and there's 150 iterations in our 117 node case. So you can probably do the math on the back of a notebook. But yeah, it does. It becomes quite quickly significant.
And each circuit was using all the 157 qubits, or however many qubits on the system?
We used 117 in our largest problem.
Thank you. Ross, go ahead.
Thanks. Yeah, this is a bit related to Amir's question. So you kind of remarked that there's a tight coupling going on here. Now, from my understanding of what you said, it seems that you could actually just stop at the end of each stage and come back next week, and it wouldn't actually harm the algorithm. So what is the tight coupling?
So generally for an MCMC procedure, you could technically pause the experiment and sort of restart it next week if you really wanted to, but that would mean that even the runtime of these sorts of experiments on a classical sense, that they would never usually take that long. And obviously, I think that the idea would be eventually that we would try and solve a problem that wasn't solved to optimality with a classical solver, and that would quite quickly take a very, very long time if we were to pause it every time we were to sort of stop the experiment. So the idea is usually that you sort of take advantage of the configuration window that the computer has been configured to just now, and ideally benefit from the same sort of error rates for the general time. The estimation for the number of shots taken per iteration is determined by the error rates per gate for the circuit you've compiled. So the longer that you leave that, the less relevant that sort of estimation becomes, and the longer and longer it would take to run the experiment. So these experiments, both for the classical and quantum sense, for the iterations that we used, it was on the scale of hours. I think we were sort of, our longest run time was on the scale of sort of 8 hours in one session, and that's with sort of streaming parameters as close as we could. So if we were to then sort of look at stopping re-queuing, I mean, that would quite quickly become sort of, there'd be no point running it at that point unless we were convinced that next year it would solve the problem.
So the parameter drift is bad enough on this hardware that this would throw your experiment off within timescale of 24 hours. But
I mean, I guess you could continue, but you would be there for a very, very long time, because I mean, 150 iterations when you re-queue a job every time. I mean, it could be up to sort of on the scale of hours to re-queue your job. So you would be with less of a guarantee that you were actually ever going to reach the global optima. You would be running for a very, very long time scale. But I guess you could if you really, if the priority was solving the problem and not the execution time.
okay, yeah, that clears it up for me. Thanks very much.
Anybody else has questions? I have a couple, but can yield the floor to others. All right, one follow-up to this one. You didn't have access to the quantum machine or the quantum computer all the time, so you had to re-queue your like jobs. Generally, I mean, like how long did the queuing on the system take until your job actually got time on the machine?
I mean, because I'm an internal user, I had a fairly favorable account for this work. So I was still on the scale of hours, but probably still quite favorable from general queue times. And once I started the experiment, we had an open session. So we had the device reserved for the rest of the experiment duration. So we used Qiskit runtime session mode to run the experiment. So it meant that once we opened our experiment window, it continued until completion. So the queuing time was always at the beginning. And then our session was open for re-queuing jobs within that window. And I think that was usually on the scale of sort of, we would submit and we would be running within 24 hours, usually within less than 6.
Cool. And have you guys thought about fault tolerant execution and how that would impact this type of experiment? Is it just going to be less number of shots?
It would definitely be less number of shots. Yeah, that would probably be the biggest change for this. And hopefully not much else of the workflow would change in this case, because it would largely just be the noise mitigation strategies, and ideally fewer iterations required as well, because the quality of the solutions would improve.
Sure, and then, but you'll still need the error mitigation
No, ideally not.
No, you'll eliminate that. Okay. Cool. That's all I had. Does anybody else have any other questions or comments? Well, great. Thank you, Kate, for your time. Really appreciate it. It was an interesting presentation. Thank you, everyone, for attending.
No worries. Thank you so much for having me.